and open portable universal skeleton. This document provides a complete technical specification of the Open Dynamic Anthropic Renderer Architecture, ODARA, a revolutionary approach to real-time graphics. This document provides a Open Dynamic Open Dynamic Anthropic Renderer Architecture and Replaceable Skeleton Architecture. A comprehensive technical reference. Version 3.0. MiLOandOpUS Framework. Minimal lightweight optimized and open portable universal skeleton. This document provides a complete technical specification of the Open Dynamic Anthropic Renderer Architecture, ODARA, a revolutionary approach to real-time graphics that prioritizes transparency, security, and extensibility over traditional hidden rendering pipelines. Unlike conventional WebGL applications that operate within opaque frames or black box rendering contexts, ODARA exposes its entire rendering pipeline to inspection, modification, and verification. This transparency-first approach ensures that users and developers can fully understand, audit, and trust the rendering system. 1. Executive Summary. The Open Dynamic Anthropic Renderer Architecture represents a paradigm shift in how we think about real-time graphics rendering. Traditional approaches high complexity behind abstractions, creating security vulnerabilities and limiting extensibility. ODARA inverts this model. Open Dynamic Anthropic Renderer Architecture, Open Dynamic Anthropic Renderer Architecture, and Replaceable Skeleton Architecture, a comprehensive technical reference version 3.0 MiLOandOpUS Framework, minimal lightweight. Optimized and open portable universal skeleton. This document provides a complete technical specification of the Open Dynamic Anthropic Renderer Architecture, ODARA, a revolutionary approach to real-time graphics that prioritizes transparency, security, and extensibility over traditional hidden rendering pipelines. Unlike conventional WebGL applications that operate within opaque frames or black box rendering contexts, ODARA exposes its entire rendering pipeline to inspection, modification, and verification. This transparency-first approach ensures page 1 of 63 Open Dynamic Anthropic Renderer Architecture that users and developers can fully understand, audit, and trust the rendering system. Page 2 of 63.1. Executive Summary. Open Dynamic Anthropic Renderer Architecture. The Open Dynamic Anthropic Renderer Architecture represents a paradigm shift in how we think about real-time graphics rendering. Traditional approaches hide complexity behind abstractions, creating security vulnerabilities and limiting extensibility. ODARA inverts this model. 1.1 Core Philosophy. ODARA is built on 3 foundational principles that guide every architectural decision. Transparency over obscurity. Every operation in the rendering pipeline is visible and inspectable. There are no hidden frames, no obfuscated shaders, and no black box transformations. Users can observe exactly how their data flows through the system. Security through visibility. By making the entire pipeline observable, ODARA eliminates entire classes of security vulnerabilities. Hidden frames have historically been vectors for clickjacking, data exfiltration, and malicious code injection. ODARA's transparent architecture makes such attacks impossible by design. Extensibility via replacement. Rather than providing fixed extension points, ODARA allows any component to be replaced entirely. The skeleton architecture means that the core rendering system is simply a reference implementation that can be swapped for alternatives. 1.2 Why not hidden frames? Hidden frames have been the traditional approach for embedding complex rendering systems, but they introduce significant problems. 1. Security vulnerabilities. Hidden frames can be exploited for clickjacking attacks. 2. Opacity. Users cannot verify what code is executing within the frame. Page 3 of 63 Open Dynamic Anthropic Renderer Architecture. 3. Cross-origin restrictions. Communication across frame boundaries is limited and complex. 4. Performance overhead. If frame boundaries create additional rendering and memory costs. 5. Debugging difficulty. Errors within frames are harder to trace and diagnose. ODARA eliminates all of these concerns by operating in a fully transparent, inspectable manner within the main document context. Page 4 of 63.2. Architecture Overview. Open Dynamic Anthropic Renderer Architecture. The ODARA system consists of 4 primary layers that work together to provide a complete rendering solution. 2.1 Layer Architecture. Layer Description Orchestration. Claude AI provides research, synthesis, and iterative improvement logic. JavaScript Engine handles rendering, entity management, and scene graphs. Bridge Frame Synchronized Relay between JS and Unity for physics integration. 2 Data Flow. Unity provides physics simulation, mechanism animation, and native capabilities. Data flows through the system in a well-defined sequence. User input. Claude Analysis. JS Scene Description. Render Pipeline. GBuffer Composite Display. Each stage of this pipeline is fully observable. Developers can inspect the intermediate results at any point, modify the processing logic, or replace entire stages with custom implementations. 2.3 The skeleton concept. At the heart of ODARA lies the skeleton, a minimal, replaceable core that provides essential rendering functionality without imposing architectural constraints. The skeleton defines interfaces, not implementations, provides reference implementations for all interfaces, allows any component to be replaced at runtime, Maintains compatibility through stable interface contracts. Page 5 of 63. Open Dynamic Anthropic Renderer Architecture. This approach means that Odara is not a monolithic framework, but rather a collection of cooperating components that can evolve independently. Page 6 of 63.3. Security Model. Open Dynamic Anthropic Renderer Architecture. Security is not an afterthought in Odara, it is a fundamental architectural principle. The transparent design eliminates entire categories of vulnerabilities that plague traditional rendering systems. 3.1 Transparency. As security, traditional security models rely on obscurity, hiding implementation details to prevent attackers from understanding the system. This approach has fundamental weaknesses. Attackers eventually discover hidden vulnerabilities. Legitimate users cannot verify security properties. Security researchers cannot audit the system effectively. Odara inverts this model. By making everything visible, we enable continuous community auditing of all components, immediate detection of anomalous behavior. User verification of data handling. 3.2 Safer than hidden frames. Hidden frames present numerous security risks that Odara eliminates by design. Clickjacking prevention. Hidden frames can be positioned over legitimate UI elements to capture user clicks. Odara operates entirely within the visible document, making such attacks impossible. Data exfiltration prevention. Code within hidden frames can silently transmit data to external servers. Odara's transparent pipeline means all network operations are visible and auditable. Code injection prevention. Page 7 of 63. Open Dynamic Anthropic Renderer Architecture. Hidden frames can load and execute arbitrary code without user awareness. Odara's code execution is fully observable in the browser's developer tools. 3.3 Sandboxing model. While transparency is the primary security mechanism, Odara also implements defense in depth through careful sandboxing. Window.cp equals / all state contained in single namespace / no global pollution, no prototype modification / strict mode enforcement throughout. Page 8 of 63.4. The skeleton system. Open Dynamic Anthropic Renderer Architecture. The skeleton is the architectural foundation that makes Odara's flexibility possible. It provides a minimal, replaceable core that defines interfaces without constraining implementations. For point 1 design principles, minimal core. The skeleton includes only essential functionality. Everything else is implemented as replaceable modules that plug into the skeleton's interfaces. Interface stability. Skeleton interfaces are versioned and maintain backward compatibility. This ensures that custom components continue to work across skeleton updates. Hot replacement components can be replaced at runtime without restarting the rendering system. This enables live development, A/B testing, and graceful degradation. For point 2 core skeleton components, component responsibility. Entity system creates, manages, and destroys scene entities with transform hierarchies. Transform manager handles parent-child relationships and world matrix computation. Segment pool allocates and recycles segment IDs for per-object rendering. Camera system manages view and projection matrices for rendering. Render pipeline executes the rendering sequence from scene graph to pixels. Gbuffer stores intermediate rendering data for deferred processing. 3 Replacement mechanism. Any skeleton component can be replaced by providing an object that implements the same interface. Page 9 of 63. Open Dynamic Anthropic Renderer Architecture / replace the default camera system. Skeleton.camera equals my custom camera system. / replace the entire render pipeline. Skeleton.render pipeline equals my custom pipeline. The skeleton verifies interface compliance at replacement time, ensuring that custom components will integrate correctly with the rest of the system. Page 10 of 63.5. Entity system. Open Dynamic Anthropic Renderer Architecture. The entity system provides a flexible, hierarchical representation of scene objects. Unlike traditional scene graphs that impose rigid structures, Odara's entity system is designed for dynamic composition and runtime modification. 5. One entity structure. Each entity in the system contains entity equals ID, number, / unique identifier name, string, / human readable name segment ID, number, / rendering segment assignment transform, local position, X, Y, Z, local rotation, X, Y, Z, W, / quaternion local scale, X, Y, Z, parent, entity ID null, children, entity ID, world matrix, float 32 array, 16, components, / extensible component storage 5.2 hierarchical transforms entities, form a tree structure through parent-child relationships. When a parent entity moves, all children move with it while maintaining their local offsets. The transform system uses lazy evaluation. World matrices are only recomputed when needed, and the dirty flag propagates through the hierarchy to ensure consistency. Set parent, child ID, parent ID, / establish hierarchy set local position, ID, X, Y, Z, / move relative to parent get world position, ID, / get absolute position page 11 of 63 5.3 entity lifecycle open dynamic anthropic renderer architecture entities follow a defined lifecycle. 6. Creation. Entity allocated with unique ID and segment ID 7. Configuration, transform, components, and hierarchy established 8. Active, entity participates in rendering and updates 9. Destruction, entity removed, segment ID recycled page 12 of 63 open dynamic anthropic renderer architecture 6. Segment-based rendering. Odara introduces a revolutionary segment-based rendering approach that enables per-object effects, efficient picking, and flexible compositing. 6.1 What are segments? A segment is a unique identifier assigned to each renderable object. During rendering, each pixel records which segment it belongs to, enabling powerful post-processing capabilities. Per-object shading. Apply different effects to different objects, pixel-perfect picking. Identify exactly which object is under the cursor, selective rendering. Show, hide objects without scene graph modification. Outline effects. Draw outlines around selected objects. 6.2 Segment pool. The segment pool manages segment ID allocation and recycling. Segment pool equals max segments 167777216 / 24-bit color equals 16 segments allocated. Set free metadata map alloc meta / get new segment ID free ID / return segment ID get meta ID / get segment metadata. 6.3 Per segment shaders. Each segment can have its own shader applied during compositing. Set segment shader segment ID / GLSL fragment shader color equals base color asterisk vec4 1.0 0.8 0.6 1.0 page 13 of 63 color. RGB asterisk equals lighting. Open dynamic anthropic renderer architecture. If selected color.rgb plus equals 0.2, this enables effects like highlighting selected objects, dimming inactive objects, or applying artistic effects to specific scene elements. Page 14 of 63.7. Gbuffer architecture. Open dynamic anthropic renderer architecture. The Gbuffer geometry buffer is a collection of screen space textures that store intermediate rendering data. This deferred approach enables complex lighting and effects without per-object overhead. 7.1 Buffer channels. Buffer format contents color RGBA 8 final pixel colors after compositing depth float 32 normalized depth values 0.0 equals near 1.0 equals far. Normal RGB8 world space surface normals packed segment uint 16 segment ID for each pixel material RGBA8 roughness metallic emission. AO motion RG16 7.2 rendering pipeline per pixel motion vectors. The deferred rendering pipeline proceeds in stages. 10. Geometry pass. Render all objects, writing to gbuffer 11. Lighting pass. Compute lighting using gbuffer data 12. Segment pass. Apply per segment shaders 13. Composite pass. Combine all layers into final image 14. Post-process pass. Apply screen space effects, SSAO, bloom, etc. 7.3 Accessing gbuffer data. The gbuffer is fully accessible to custom code. // read depth at pixel var depth equals window.cp.depth y asterisk width plus x. // read segment ID at pixel var segment equals window.cp.segment ID y asterisk width plus x. // modify final color window.cp.pixels y asterisk width plus x. Asterisk 4 plus 0 equals red. Page 15 of 63 Open Dynamic Anthropic Renderer Architecture. Page 16 of 63-8. Render modes. Open Dynamic Anthropic Renderer Architecture (ODARA) supports multiple rendering modes to accommodate different use cases and performance requirements. 8.1 Mode 1. Scene Graph. Rendering. The scene graph mode renders entities based on their hierarchical organization. This is ideal for structured scenes with clear object relationships. // scene graph mode skeleton. Render mode equals scene graph // rendering traverses the entity tree function render scene graph root render entity root 4 var child of root.children render scene graph child. 8.2 Mode 2. SDF ray marching. The SDF sign distance function mode uses ray marching to render implicit surfaces. This enables smooth organic shapes and complex Boolean operations. // SDF ray marching mode skeleton. Render mode equals SDF // define SDF primitives function SDF sphere p center radius return length p center radius. // combine with smooth union function SDF smooth union d1 d2 k var h equals clamp 0.5 plus 0.5 asterisk d2 d1 / k 0 1 return mix d2 d1 h k asterisk h asterisk 1 h. Page 17 of 63 Open Dynamic Anthropic Renderer Architecture 8. 3 Hybrid mode. The hybrid mode combines scene graph and SDF rendering, allowing traditional meshes and implicit surfaces to coexist in the same scene. // hybrid mode skeleton. Render mode equals hybrid // meshes rendered first. SDFs composited render scene graph root raymark SDFs composite results. Page 18 of 63-9. Mesh synthesis. Open Dynamic Anthropic Renderer Architecture (ODARA) includes a powerful mesh synthesis system that can generate 3D geometry from various inputs, enabling procedural content creation and AI-driven modeling. 9.1 Bone-based mesh generation. The primary mesh synthesis method uses bone chains to define organic shapes. Var mesh equals mesh from bones, PUS, 0, 0, 0, radius, 0.1, // head PUS, 0.5, 0, 0, radius, 0.3, // body PUS, 1.5, 0, 0, radius, 0.2, // tail PUS, 2.0, 0, 0, radius, 0.05 // tip, 0. 232 // smoothing segments. This approach creates smooth, organic meshes ideal for characters, creatures, and natural objects. 9.2 SDF to mesh conversion. Implicit SDF surfaces can be converted to explicit meshes using marching cubes. // define SDF function mySDF x, y, z, return sphere SDF x, y, z, 1.0, noise SDF x, y, z, 0.2, // convert to mesh var mesh equals SDF to mesh, mySDF, bounds, -2, -2, -2, 2, 2, 2, resolution, 64. 9.3 Research-driven generation. Claude can research real-world objects and synthesize appropriate meshes. Page 19 of 63. Open Dynamic Anthropic Renderer Architecture. / Claude researches Dolphin and generates synthesize mesh, Dolphin, anatomical accuracy, 0.8, stylization, 0.3, detail, medium, page 20 of 6310. Lighting system. Open Dynamic Anthropic Renderer Architecture. ODARA implements a deferred multi-light system that supports unlimited dynamic lights without per-object overhead. 10. 1 light types. Type description. Point omnidirectional light emanating from a single point with distance. Fall-off spot. Conical light with position, direction, angle, and fall-off. Directional parallel rays simulating infinitely distant light source, sun. Area. Rectangular or disc-shaped emitter for soft shadows. 10.2 Light properties. Add light type spot POS 5 8 0 DR 0 -1 0 color 1.0 0.9 0.8 intensity 2.0 radius 15 angle 30 cast shadow true segment mask 1 5 12 / only affects these segments. 10.3 Dynamic GLSL generation. The lighting system generates optimized GLSL code for the current light configuration. var lighting GLSL equals get lighting GLSL / returns shader code for all active lights. Set segment shader segment ID. Lighting GLSL plus. Page 21 of 63. Open Dynamic Anthropic Renderer Architecture. Color equals base color * vec4. Total light 1.0. Page 22 of 6311. Procedural animation. Open Dynamic Anthropic Renderer Architecture. ODARA includes a comprehensive procedural animation system that generates natural motion without keyframe data. 11.1 Inverse kinematics. The fabric, forward and backward reaching inverse kinematics. Solver enables characters to reach for targets. / define bone chain. Var arm chain equals POS 0 1.5 0 / shoulder POS 0.3 1.5 0 / elbow POS 0.6 1.5 0 / wrist / solve for target. Var new positions equals solve IK arm chain target pos 10. 11.2 Spring physics. Secondary motion is handled through spring dynamics. Add spring ponytail stiffness 80 damping 8 mass 0.5 / update each frame. Var hair pos equals update spring ponytail head pos DT 11. 3 Motion generators. Walk cycle. Page 23 of 63. Open Dynamic Anthropic Renderer Architecture. Var pose equals walk cycle time speed amplitude / returns hip L hip R spine arm L arm R. Breathing. Var breath equals breathe time rate depth / returns chest belly. Scale factors. Idle fidget. Var fidget equals fidget time intensity / returns noise-based subtle movements. Page 24 of 6312. Temporal effects. Open Dynamic Anthropic Renderer Architecture. ODARA provides temporal processing capabilities that use information from multiple frames to enhance visual quality. 12.1 Frame history. The temporal system maintains a buffer of previous frames. Temporal equals frame history max history 4 prev frame data null / capture before rendering capture frame. 12.2 Motion blur. Velocity-based motion blur uses frame history to create smooth motion. / apply motion blur 0.0 to 1.0 strength motion blur 0. 3. The blur is computed per pixel based on the difference between current and previous frame positions. 12.3 Temporal anti-aliasing. TAA blends the current frame with history to reduce aliasing. / apply TAA 0.0 to 1.0 blend factor TAA blend 0.15. Page 25 of 6312.4 Ghost Trail Effect Open Dynamic Anthropic Renderer Architecture creates afterimage effects for fast-moving objects. / Ghost Trail 0.0 to 1.0 decay rate. Ghost Trail 0.85. This effect is particularly useful for action sequences, special attacks, or artistic stylization. Page 26 of 6313. Particle System Open Dynamic Anthropic Renderer Architecture ODARA includes a high-performance particle system capable of simulating thousands of particles with physics and rendering integration. 13.1 System Creation Create Particles. Fire, count, 5,000, emit rate, 200, emit pos, 0, 0, 0, emit dr, 0, 1, 0, emit spread, 0.3, emit speed, 2, 5, life range, 0.5, 2, size range, 0.02, 0. 1, gravity, 0, 2, 0, / upward for fire color, 1, 0.5, 0.1, 13.2 Particle data layout for cache efficiency. Particle data is stored in structure of arrays format. System equals POSX. Float 32 array count POSI. Float 32 array count POSC. Float 32 array count VELX. Float 32 array count VELY. Float 32 array count VELZ. Float 32 array count life. Float 32 array count size. Float 32 array count 13.3 Runtime Control Page 27 of 63 / Manual Burst. Emission Open Dynamic Anthropic Renderer Architecture Emit Particles. Fire 100 POS. Explosion point / update physics each frame update particles. Fire delta time. / render to gbuffer with segment ID render particles. Fire page 28 of 6314. Audio Reactive System Open Dynamic Anthropic Renderer Architecture ODARA can analyze audio input and drive visual parameters in real time, enabling music visualization and reactive effects. 14. 1 Audio Analysis. The system uses Web Audio API for frequency analysis. / connect to audio element init audio, document.query selector, audio / update each frame update audio, / get frequency bands var bands equals get audio bands, / returns, bass, mid, high, volume 14.2 beat detection. Automatic beat detection triggers events on musical beats, if on beat. Emit particles, sparks, 50, flashlight, mainlight, 0.1, 14.3 Audio-driven shaders. Audio data can drive. Shader parameters. Set segment shader, segment ID, / audio uniforms available float pulse equals U_base * 0.5 plus 0.5, float shimmer equals U_high * sin. U_time * 10.0, page 29 of 63 Open Dynamic Anthropic Renderer Architecture Color equals base color * pulse, color.rgb plus equals shimmer * 0.1, if U_beat greater than 0.5, color.rgb equals 1.0, color.rgb, / invert on beat, page 30 of 6315. Screen Space Effects Open Dynamic Anthropic Renderer Architecture ODARA includes several screen space post-processing effects that enhance visual quality using gbuffer data. 15.1 Screen Space Ambient Occlusion, SSO. SSO darkens creases and corners to add depth and realism. SAO equals samples. 16. / kernel samples radius. 0.5. / sample radius bias, 0.025 / depth bias, / apply after rendering compute SSAO. 15.2 Effect pipeline effects are applied in sequence. Begin frame / render scene to gbuffer skeleton.render, Render particles, effects, / apply post-processing compute SSAO, / ambient occlusion. Composite segments, / per segment shaders motion blur, 0.2, / temporal effects TAA blend, 0.1 end frame. Page 31 of 6315.3 Custom Post-Processing Open Dynamic Anthropic Renderer Architecture Developers can add custom screen space effects. Function Custom Vignette var w equals window.cp w h equals window.cp.h var pixels equals window.cp.pixels 4 var y equals 0 y less than h y plus plus 4 var x equals 0, x less than w, x plus plus. Var dx equals x/w 0.5, dy equals y/h 0.5, var vignette equals 1, dx asterisk dx plus dy asterisk dy, var I equals y asterisk w plus x, asterisk 4. Pixels, I, asterisk equals vignette, pixels I plus 1, asterisk equals vignette, pixels I plus 2, asterisk equals vignette, page 32 of 63 Open Dynamic Anthropic Renderer Architecture 16. Network synchronization Odara includes a comprehensive networking layer that enables multiplayer experiences, bot coordination, and spectator modes. 16.1 Connection Model The network system uses WebRTC for peer-to-peer communication with a lightweight signaling server, init network, peer ID, player underscore plus random ID, role, player, / player, bot, spectator, host is host, true, signaling URL, wsys, / signal.example.com 16. Two entity ownership entities are owned by specific peers, preventing conflicts, / claim control of entity claim entity, player.id, / check ownership before modifying if owns entity. Enemy.id, set position, enemy.id, new pos, / release for others to claim release entity. Item.id. 16.3 Transform synchronization entity transforms are synchronized with delta compression. / in frame loop page 33 of 63 Open Dynamic Anthropic Renderer Architecture sync transforms, / send. Owned entity transforms interpolate remote, / smooth, remote entities the system only sends transforms that have changed, with quantization for bandwidth efficiency. Page 34 of 6317. Selective sharing Open Dynamic Anthropic Renderer Architecture Odara enables fine-grained control over what data is shared and with whom, supporting team-based games, private communications, and selective visibility. 17. One sharing scopes data can be shared with specific audiences. Scope recipients, all connected peers, players, only peers with role, player, bots, only peers with role, bot, spectators, only peers with role, spectator, team, red. Only peers on team, red, ID1, ID2. Specific peer IDs only 17.2 shareable content types code snippets share code. Ability _ fire. Emit particles, fire, 100. Players, shader share shader. Team _ glow, color dot, R plus equals 0.3, team, red. Description share description, objective, capture the flag. All 17.3 channels provide private rooms for team communication. Create channel, strategy, password. Secret 123 join channel, strategy. Secret 123 share to channel. Strategy, code, formation, V-shape, page 35 of 6318. Bot System Open Dynamic Anthropic Renderer Architecture Odara includes a sophisticated bot system for AI-controlled entities, supporting various behaviors and swarm coordination. 18. One bot creation var guard equals create bot, guard, AI, patrol set bot patrol, guard.entityId, 0. 0, 0, 10, 0, 0, 10, 0, 10, 0, 0, 10. 18.2 AI behaviors. Behavior description: idle, stand still. No movement, wander, move randomly within an area, follow a target entity, patrol, move between waypoints in sequence, custom execute, custom update function. 18.3 Swarm coordination. Multiple bots can be coordinated using swarm behaviors. Leader following. Leader follow, leader read, bot 1, bot 2, bot 3, 2, flocking, voids, flocking, bot array. Page 36 of 63. Open dynamic anthropic renderer architecture separation. 2. Alignment. 1. Cohesion. 1. Max speed. 3. Formations. Var positions equals get formation. V-shape. Bots. 2. // also. Line. Circle. Grid. Page 37 of 6319. Spectator mode. Open dynamic anthropic renderer architecture ODARA provides a comprehensive spectator system for observers, broadcasters, and replay viewing. 19.1 Camera modes. Mode description: third-person camera following behind the target. First-person view from target's perspective. Orbit. Camera orbits around the target automatically. Free camera movement not attached to target. 19.2 Target cycling. Spectators can cycle through viewable entities. Spectator cycle next, / next entity. Spectator cycle prev, / previous entity. Spectator follow. Specific entity ID, / lock to entity. 19.3 Visibility filters. Spectators can filter what they see. Spectator.filters equals showbots, true, show players, true, show particles, true, highlight followed, true. 19.4 Integration / spectator frame loop. If get my role equals. Spectator. Page 38 of 63. Spectator update. DT. Open dynamic anthropic renderer architecture / spectators receive all data but cannot modify / they see shared code / shaders but cannot claim entities. Page 39 of 6320. Unity integration. Open dynamic anthropic renderer architecture ODARA integrates with Unity for physics simulation, mechanism animation, and native platform capabilities, while maintaining JavaScript control of the rendering pipeline. 20.1 Frame synchronization. The frame relay ensures JS and Unity stay synchronized. / Unity side, C#, void update, send message, frame start, time.delta time. / wait for JS to process / apply physics results, send message, frame end / JavaScript side on Unity event, frame start, function, DT, begin frame, update logic, DT on Unity event, frame end, function, end frame. 20.2 Authority control. Each entity has a designated authority, JS or Unity / JS controls position. Unity simulates physics set authority, entity ID, position, JS set authority, entity ID, physics, Unity. Page 40 of 6320. 3. Physics integration. Open dynamic anthropic renderer architecture / request physics simulation from Unity sync to Unity, entity ID. / send current state / receive physics results on Unity event, physics result, function, data, apply physics result, data.entity ID, data.velocity. Page 41 of 6321. GL Mesh Pipeline. Open dynamic anthropic renderer architecture ODARA includes a complete WebGL mesh rendering pipeline that integrates with the segment-based gbuffer system. 21.1 Mesh upload. Var mesh equals vertices, new float 32 array, / POS, normal, UV, color indices, new uint 16 array, var GL mesh equals upload mesh, add mesh component, entity ID GL mesh, 21.2 vertex format. Each vertex contains attribute size, purpose, position 3 floats, world space, vertex position, normal 3 floats, surface normal for lighting, UV 2 floats, texture, coordinates, color 4 floats. 21. 3G buffer integration. Vertex color R G B equals segment ID GL meshes write to the same gbuffer as software rendering. // vertex color encodes segment ID GL_frag color equals vec4. Float, segment ID and 0xFF. /255.0, float, segment ID 8, and 0xFF. /255.0, float, segment ID 16, and 0xFF. /255.0, 1.0, page 42 of 63 Open Dynamic Anthropic Render Architecture. This allows hardware-accelerated meshes to participate in per-segment shading and compositing. Page 43 of 6322. Camera System Open Dynamic Anthropic Render Architecture ODARA provides flexible camera control supporting multiple projection modes and rendering approaches. 22.1 Camera Configuration Skeleton.camera equals POS 0, 5, 10, target 0, 0, 0, up 0, 1, 0, FOV 60, / degrees for perspective near 0.1, far 1000, mode, perspective / or orthographic, equirectangular 22. 2 projection modes perspective standard 3D perspective with depth foreshortening. Most common for games and 3D visualization. Orthographic parallel projection without perspective distortion. Useful for 2D games, technical visualization, and UI. Equirectangular 360-degree panoramic projection. Enables VR viewing and environment mapping without re-rendering. 22.3 Camera Movement page 44 of 63 / smooth follow camera open dynamic anthropic render architecture function update camera target DT var POS equals get position target skeleton.camera.target equals lerp skeleton.camera.target POS 5 * DT skeleton.camera.pos equals POS 0 5 POS 1 + 3 POS 2 5. Page 45 of 63 Open Dynamic Anthropic Render Architecture 23. Research-driven synthesis. One of ODARA's unique capabilities is the integration of AI research into the rendering pipeline. Claude can research topics and synthesize appropriate visual representations. 23.1 The research workflow 15. User requests a visual element, e.g., create a dolphin. 16. Claude researches the subject using available knowledge. 17. Key features are identified, proportions, colors, distinctive elements. 18. Appropriate mesh synthesis method is selected. 19. Geometry is generated with semantic understanding. 20. Materials and shaders are assigned based on research. 23.2 Iterative improvement the system supports. Propose test hybrid iterate cycles. / Claude proposes in implementation var proposal equals synthesize dolphin style realistic / test renders for evaluation var test result equals test render proposal / hybrid combines best elements var hybrid equals hybridize proposal existing version weights 0.7 0.3 / iterate until satisfactory iterate hybrid max iterations 523. 3 Knowledge integration. Claude brings real-world knowledge to visual synthesis. Page 46 of 63 Open Dynamic Anthropic Render Architecture Anatomical accuracy for creatures and characters, architectural proportions for buildings, physical properties for materials, historical accuracy for period pieces. Page 47 of 63 Open Dynamic Anthropic Render Architecture 24. Performance optimization. ODARA is designed for real-time performance while maintaining flexibility and transparency. 24.1 Frame budget at 60 FPS. Each frame has approximately 16.67 milliseconds to complete all processing. Stage budget optimization scene update 2 milliseconds dirty flags. Spatial hashing geometry past 6 milliseconds frustum culling. LED lighting pass 3 milliseconds light culling, tiled shading post-processing 3 milliseconds half resolution. Temporal present 2 milliseconds, 24.2 optimization techniques, lazy evaluation, async transfer world matrices are only recomputed when transforms change. The dirty flag system ensures minimal recalculation. Spatial hashing entities are organized spatially for efficient culling and neighbor queries. Object pooling segment IDs, particles, and temporary objects are pooled rather than allocated/freed each frame. Delta compression network synchronization only sends changed values with quantization for bandwidth efficiency. Page 48 of 6324.3 Profiling Open Dynamic Anthropic Renderer Architecture / Enable Profiling Skeleton.profiling equals true / access timing data console.log skeleton.timing / update 1.2 render 5.8 post 2.1. Page 49 of 6325. Usage Budget System Open Dynamic Anthropic Renderer Architecture ODARA includes a comprehensive cost tracking and budget management system that allows users to set spending limits and automatically scales quality to stay within budget. 25.1 Configuration Init Budget Max Cost Per Minute 0.10 / 10 cents per minute cap max cost per hour 5.00 / $5 per hour cap max cost per session 20.00 / $20 per session cap warning threshold 0.8 / warn at 80%. 25.2 Cost Rates Default Rates Configurable per deployment operation default rate example Claude input token $0.000003 tokens Claude output token $0.000015 $1 tokens render frame $0.00000010.006 per minute at 60 frames per second mesh synthesis $0.001 $1 / 1000 meshes. Network sync $0.00001 25.3 automatic tracking / called automatically in frame loop $0.012 per minute. At 20 Hz track frame / per frame track Claude input tokens output tokens / after API call track mesh synthesis / per mesh generated track network / per sync operation track particles batch size / per particle update track audio / per audio analysis page 50 of 6325. For budget-aware quality scaling Open Dynamic Anthropic Renderer Architecture the system automatically calculates a quality scale based on remaining budget. var scale equals get quality scale / 0.1 to 1.0 / get recommended settings based on budget var settings equals get recommended settings / returns / particle count 100 1000 / light count 1 to 8 / shadow quality low medium high / SEO samples 4 to 16 / sync rate 5 to 20 / Claude token limit 500 4000 / 25.5. Pause and resume when limits are reached. The system automatically pauses / check status if is budget paused console.log paused waiting for budget reset / wait for minute to rollover then resume budget / only works if under limits / user override add more budget force resume budget 5.00 / add $5 to session limit 25.6 callbacks set budget callback on warning function type ratio console log warning plus Ratio asterisk 100 plus % of plus type plus limit, page 51 of 63. Open dynamic Anthropic renderer architecture. Set budget callback. On limit reached, function, reason. Show modal. Budget limit reached, plus reason. Set budget callback. On pause, function, reason. / reduce quality. Show waiting screen. Set budget callback. On resume, function. / restore quality. Hide waiting screen. 25.7 reporting print budget report. / equals budget report equals / status. Active / session total. $0.0523 / $20.0000 this hour. $0.0412 / $5.0000 this minute. $0.0089 / $0.1000 average / min. $0.0104 / quality scale. 92% / breakdown. Claude. 0.03. Render. 0.01. var remaining equals get budget remaining. / minute. 0.0911. Hour. 4.9588. Session. 19.9477, page 52 of 6326. Extending Odara. Open Dynamic Anthropic Renderer Architecture. Odara is designed to be extended through component replacement, custom shaders, and plugin systems. 26. 1 custom components. Any skeleton component can be replaced with a custom implementation. / custom camera system with VR support. Skeleton.camera equals skeleton.camera mode VR left eye, right eye. Update function DT / custom VR camera logic. 25.2 custom render passes. Additional render passes can be inserted into the pipeline. Skeleton.renderPipeline.addPass custom outline. Order after segment execute. Function gbuffer / draw outlines around selected objects for var ID of selected segments. Draw outline gbuffer ID outline color. Page 53 of 63. 25.3 plugin system. Open Dynamic Anthropic Renderer Architecture / register plugin. Odara.register plugin. Weather init. Function skeleton. Update function DT. Render function gbuffer / enable plugin Odara. Enable plugin. Weather. Page 54 of 63. Open Dynamic Anthropic Renderer Architecture. 26. API reference summary. 26.1 entity functions. Create entity name, entity destroy entity ID, get entity ID, entity set position ID X Y Z, get position ID X Y Z, set rotation ID X Y Z / Euler degrees, set parent child ID parent ID. 26.2 rendering functions. Begin frame, end frame, skeleton.render, composite segments, set segment shader, segment ID. GLSL. 26.3 lighting functions. Add light, config, light ID, remove light ID, set ambient, RGB, get lighting. GLSL. String. 26.4 animation functions. Solve IK, chain, target, iterations, positions. Add spring ID, config, update spring ID, target, DT, position, walk cycle, T, speed, amplitude, pose, breathe, T, rate, depth. Scales. Page 55 of 6326. 5 network functions. Open Dynamic Anthropic Renderer Architecture. Init network, config, peer ID, claim entity ID, release entity ID, sync transforms, interpolate remote, share code ID, code, scope, share shader ID. GLSL scope. Page 56 of 6327. Best practices. Open Dynamic Anthropic Renderer Architecture. 27.1 Scene organization. Use hierarchical entity structures for logical grouping. Assign meaningful names to entities for debugging. Group related objects under common parents for batch operations. Use segment IDs to organize objects by material or effect. Needs 27.2 performance. Minimize transform updates. Batch changes when possible. Use LOD. Level of detail. For distant objects, pool frequently created/destroyed. Objects profile regularly. Optimize bottlenecks. 27.3 networking. Only sync entities that need network visibility. Use appropriate scopes for shared resources. Implement prediction for responsive gameplay. Handle disconnection gracefully. 27. For security, validate all received network data. Don't auto-execute shared code from untrusted peers. Use channels with passwords for sensitive communication. Audit shared shaders before applying. 27.5 transparency. Keep all code inspectable. Avoid obfuscation. Document custom components thoroughly. Log significant operations for debugging. Enable users to inspect the rendering pipeline. Page 57 of 63. Open Dynamic Anthropic Renderer Architecture. Page 58 of 63. Open Dynamic Anthropic Renderer Architecture. 28. Comparison with traditional approaches. Odara represents a fundamental departure from traditional rendering architectures. This section compares key differences. 28.1 Hidden of Frame versus Odara Aspect. Hidden of Frame. Odara Code Visibility. Hidden opaque, fully inspectable security model. Obscurity-based, transparency-based, clickjacking, risk high, none data exfiltration possible, auditable debugging, difficult, standard tools, extensibility limited, complete replacement, trust model, blind trust. 28.2 Traditional Engine versus Odara. Verify everything aspect. Traditional engine. Odara architecture. Monolithic, composable skeleton extension plugin points component. Replacement pipeline. Fixed stages. Configurable AI integration add-on. Native runtime. Modify limited. 28.3 The safety advantage. Hot replacement. Odara's transparent design provides safety guarantees that hidden approaches cannot match. All code is inspectable in browser developer tools. Network traffic is visible and auditable. No hidden execution contexts. Users can verify exactly what is running. 28. For malicious code generation filtering. When AI systems generate code for the rendering pipeline, multiple layers of implemented failsafes prevent malicious output. Page 59 of 63. Open Dynamic Anthropic Renderer Architecture. Static Analysis. Security.analyze code. Pattern blocking. 17 plus regex patterns detect dangerous constructs. Eval. Function constructor. DUM manipulation. Network requests. Prototype pollution. Size limits. Code exceeding 100 kilobytes is rejected. Infinite loop detection. While true, and 4 winky face patterns flagged. // blocked patterns include blocked patterns /eval /s // no nested eval /function /s */ no function constructor /document /dot write cookie // no DM /cookie access /local storage session storage // no storage access /fetch /s */ xml http requests // no network requests __proto_prototype /s */ no prototype pollution // 11 more patterns. Sandboxed execution. Security.sandboxedexec. Isolated context. Code runs with controlled globals only. Math. JSON. Console. Odara API. Loop instrumentation. All loops get iteration counters. Max 100,000 iterations. Timeout enforcement. Execution limited to 1,000 milliseconds by default strict mode. All sandboxed code runs in JavaScript strict mode // sandboxed execution. Example var result equals sandboxed exec. Code. Network. Peer. 123 // returns. Success. Bool. Result. Any. Time. MS error. String, trust level system, security. Set trust/get trust, full, code analyzed and executed in sandbox, limited, code analyzed and stored, but not executed, none, code stored for inspection only, default for unknown peers, expiring trust. Trust can auto-expire after specified duration // trust management set trust, peer _ ABC 123, full, 360, 0000. / trust for 1 hour var level equals get trust, peer _ ABC 123 / full, revoke trust, peer _ ABC 123. / immediate revocation, page 60 of 63 Open Dynamic. Anthropic renderer architecture code signing, security.sign code / verify signature, HMC style signatures for code origin verification, signature verification before execution of signed code audit logging, security.get audit log, all security events logged with timestamps, actions, analyze, blocked, success, error, timeout, trust set, trust revoked, rolling buffer of 1,000 entries for forensic review, prototype protection. Security.freeze prototypes, object. Freeze on object, array, string, number, function prototypes prevents prototype pollution attacks from any code path. These layered failsafes ensure that even when AI generates code dynamically, the system maintains security guarantees that exceed those of static, pre-written applications. Page 61 of 6329. Conclusion. Open Dynamic Anthropic Renderer Architecture. The Open Dynamic Anthropic Renderer Architecture represents a new paradigm in graphics programming, one that prioritizes transparency, security, and extensibility without sacrificing performance or capability. By making the entire rendering pipeline visible and replaceable, Odara enables a level of trust and customization that traditional approaches cannot provide. Users and developers can verify exactly what code is executing, audit data handling and network communication, replace any component with custom implementations, extend capabilities through standard interfaces. Integrate AI-driven content creation. The replaceable skeleton architecture ensures that Odara can evolve without breaking existing implementations. New rendering techniques, optimization strategies, and integration patterns can be adopted incrementally. Most importantly, Odara demonstrates that security through transparency is not only possible, but preferable to security through obscurity. By eliminating hidden frames and opaque rendering contexts, Odara provides a foundation for graphics applications that users can genuinely trust. 29.1 The MiLOandOpUS vision. MiLOandOpUS, minimal, lightweight, optimized, and open portable universal skeleton, embodies the philosophy that less can be more. By providing a minimal core that does essential things well, it creates space for infinite extension and customization. The future of graphics is open, transparent, and collaborative. Odara and MiLOandOpUS provide the foundation for that future. Page 62 of 63 Open Dynamic Anthropic Renderer Architecture. Dolphin. Page 63 of 63.